Evolving parameters of regression refers to the idea that regression model parameters are not always fixed values but can change over time, across environments, or during the learning process. Traditional regression assumes stable relationships between variables, but many real-world systems are dynamic, meaning the influence of predictors evolves as conditions change. In classical linear regression, parameters such as coefficients are estimated once using historical data and then treated as constant. This works well in static environments where relationships remain stable. However, in domains like finance, climate modeling, language processing, and adaptive control systems, relationships between variables shift due to external influences, behavioral changes, or evolving systems. In such cases, evolving parameters allow models to stay relevant and accurate. One key motivation behind evolving regression parameters is non-stationarity. Non-stationary data is data whose statistical properties change over time. For example, consumer behavior, market volatility, or sensor data streams often exhibit shifting patterns. If a model assumes fixed coefficients, it may become outdated quickly. Allowing regression parameters to evolve enables the model to adapt continuously to new data patterns. There are several approaches to modeling evolving parameters. One common method is sliding window regression. In this approach, the model is retrained periodically using only the most recent data. This allows coefficients to change over time, reflecting recent trends while discarding outdated information. While simple, this method can lose long-term insights if the window is too small. Another approach involves recursive or online regression. Instead of retraining from scratch, parameters are updated incrementally as new data arrives. Recursive least squares is a classic example where coefficients are adjusted using each new observation. This approach is computationally efficient and well suited for real-time applications such as signal processing or IoT systems. State-space models provide a more formal framework for evolving regression parameters. In this formulation, regression coefficients are treated as hidden states that evolve according to a dynamic process. Techniques like the Kalman filter estimate these changing parameters over time. This approach is powerful because it explicitly models uncertainty and temporal evolution, making it useful in tracking problems in time-varying systems. Another modern perspective comes from machine learning and adaptive optimization. Neural networks, for instance, inherently learn evolving parameters during training through gradient updates. However, even after deployment, models can be designed to continue adapting via continual learning or streaming learning frameworks. This blends regression concepts with adaptive intelligence, allowing systems to remain flexible in changing environments. Regularization also plays an important role when dealing with evolving parameters. If parameters change too freely, the model may overfit short-term noise. Techniques like forgetting factors, smoothness constraints, or Bayesian priors help control how rapidly parameters evolve. This ensures the model adapts while maintaining stability and interpretability. Evolving regression parameters are especially valuable in real-time analytics. In financial markets, asset relationships shift due to macroeconomic changes. In robotics, sensor calibration may drift over time. In language systems, word usage evolves with cultural trends. Static models struggle in these contexts, but adaptive regression maintains relevance by continuously updating relationships. One of the main challenges with evolving parameters is balancing adaptability and stability. A model that adapts too quickly may chase noise and become unstable. A model that adapts too slowly may become obsolete. Designing mechanisms that control the speed of parameter evolution is therefore critical. This often involves tuning update rates, smoothing mechanisms, or probabilistic assumptions. Interpretability is another consideration. Traditional regression is valued for its clear coefficients that describe relationships between variables. When parameters evolve, interpretation becomes more complex because relationships are no longer fixed. Analysts may need to visualize coefficient trajectories over time or interpret parameter dynamics rather than static values. From a theoretical standpoint, evolving regression connects optimization, time series analysis, and adaptive systems. It bridges static statistical modeling and dynamic learning. This makes it particularly relevant in modern data science, where data streams are continuous and environments are rarely stable. Evolving ARMAX models refer to extensions of traditional time series models where the parameters of ARMA or ARMAX systems are allowed to change over time. These models are designed to handle non-stationary environments where relationships between past observations, noise terms, and external inputs are not constant. By allowing coefficients to evolve, ARMAX models become more flexible and better suited for real-world dynamic systems. To understand evolving ARMAX, it helps to recall the standard models. An ARMA model combines autoregressive and moving average components. The autoregressive part models a variable using its past values, while the moving average component captures dependence on past error terms. ARMAX extends this by including exogenous variables, allowing external inputs to influence the output. In classical formulations, all parameters are assumed fixed. However, many real-world processes are non-stationary. Financial volatility shifts with economic cycles, environmental data changes with seasons, and communication signals drift over time. In these situations, fixed ARMAX coefficients may fail to capture changing dynamics. Evolving ARMAX models address this limitation by allowing parameters to adapt as new data arrives. The central idea is to treat model parameters as time-dependent functions rather than constants. Instead of a single coefficient for each lag or input, the model uses coefficients that vary with time. This transforms the model into a time-varying linear system where the structure remains similar, but the influence of past values and external inputs evolves. One common approach is recursive estimation. Techniques such as recursive least squares update ARMA open parenthesis x close parenthesis parameters incrementally with each new observation. This allows the model to adapt continuously without retraining from scratch. A forgetting factor is often used, so recent data has more influence than older observations, helping the model track changing dynamics. Another powerful framework uses state space representations. In this formulation, evolving ARMA open parenthesis x close parenthesis models are expressed with hidden states representing time-varying coefficients. Filters, such as the Kalman filter, estimate these parameters dynamically by balancing prediction and correction. This approach is widely used in control systems, navigation, and econometrics because it provides a principled way to handle uncertainty and temporal variation. Sliding window estimation is a simpler alternative. The model is repeatedly re-estimated using a moving subset of recent data. This allows coefficients to change over time while maintaining computational simplicity. However, it may discard useful long-term information if the window is too short and may react slowly if the window is too large. In evolving ARMAX models specifically, external variables introduce additional complexity. The influence of exogenous inputs may vary depending on context. For example, the impact of weather on energy demand changes across seasons. All marketing campaigns influence sales differently over time. Allowing input coefficients to evolve helps capture these context-dependent relationships more accurately. Regularization and constraints are crucial in evolving ARMAX modeling. Without constraints, parameters may fluctuate excessively, leading to instability or overfitting. Smoothness constraints or Bayesian priors are often used to ensure gradual evolution. These mechanisms prevent the model from reacting too strongly to noise while still adapting to genuine changes. One of the major advantages of evolving ARMAX models is improved predictive performance in dynamic environments. Static models may degrade as system dynamics shift, but adaptive models maintain accuracy by continuously updating parameters. This makes them highly valuable in applications such as algorithmic trading, adaptive signal filtering, fault detection, and real-time forecasting.